Hello, everyone. My name is Chongqi Guan, and I'm a PhD student at Penn State University. Today, I'm going to present our work, HoneyIoT, Adaptive High Interaction Honeypot for IoT devices through reinforcement learning. I will first go through some background information here. So there exists many threats to IoT-based systems due to their inherent vulnerabilities, which may be caused by the use of outdated or broken security modules, improper patch management, or just software bugs. Just like what I listed here, it seems that from time to time, we can see some news telling us that certain model of IoT devices are being hacked and people's security and privacy is under threat. Therefore, the security challenge for IoT need to be addressed. A lot of ideas have been proposed to increase the overall security posture for IoT devices, and Honeypot is certainly one of them. Honeypots are decoy systems deployed in the network. They usually mimic certain functionalities of a real device and therefore appear to be high-value targets to the attackers. With the help of the honeypot, the defender can notice that there is an ongoing attack. They can also learn the attack behavior by looking at the attack trace collected by the honeypot. In addition, since honeypot does not have any real production value and all data is essentially fake, the attackers are wasting their time interacting with the honeypots. Problem with conventional IoT honeypot is that the attackers are evolving too. Back in 2016, the storm of Mariah botnet has overwhelmed several high-profile targets. The original Mariah botnet compromised IoT devices through brute force login against telnet port. The attacker hard-coded a few default password and username combination into the port scanner. After successful login, Mariah botnet will try to perform a series of operations to infect the target device and corral them into a botnet. However, with the upgrading of IoT devices over recent years, simple brute force logging attacks against telnet port is no longer effective. For example, some IoT devices manufacturers choose to use random default password to mitigate password cracking. Others choose to disable the telnet and SSH service by default. On the other hand, attacks against IoT devices are also evolving. For example, instead of simple password cracking, some attackers are targeting various type of vulnerabilities on the IoT devices. If there is a remote code execution vulnerability on the target device, attackers can still inject malicious code and corral the target device into their botnet. So this figure shows a typical attack process against IoT devices. The attacker first used some reconnaissance tools such as mass scan to locate the victim device. Then they scan and probe the open ports of the target device to gather more information. The responses from the remote host can be used to match known fingerprints of existing honeypots. If the attacker thinks the remote host is a honeypot, they can terminate the attack session and blacklist this IP. The response can also be used to identify the service running on the remote host, which can further be leveraged to pinpoint the type or brand model of the victim IoT devices. After identifying the remote host, the attacker can speculate what type of vulnerabilities exist on target IoT device, and then try to exploit those vulnerabilities. If they succeed, they may launch various types of follow-up attacks, such as uploading malwares or paralyzing the device. Therefore, an effective honeypot for IoT devices must pass all these pre-attack checks. So based on the background information we gave, we set up a few design goals for HoneyIoT. First, HoneyIoT need to respond to the pre-attack checks from the attackers properly, just like a real IoT device, so that it won't be identified as a honeypot. In addition, HoneyIoT should also be able to direct attackers to upload their malicious malware samples. Also, for better scalability, HoneyIoT should not require physical device at runtime. At last, HoneyIoT should be able to collect the attack log and perform preliminary analysis on the attackers. So here is a system overview for HoneyIoT, which mainly consists of three parts: the front end and the reinforcement learning agent and the response database. So I will introduce them one by one. At the very beginning, we need to collect some attack trace to build up the database. So let's go to the attack trace collection part. We design a real device-based system to learn how the attacker interacts with the IoT devices. The system consists of a front-end virtual machine running on the public cloud and different IoT devices, including various models of IoT cameras, routers, and smart plugs at the backend. The front end interacts with the attackers by forwarding any packet received to one of the IoT device. Based on the attacker's request, the corresponding IoT device sends necessary files or response back, and the front end will then forward these responses to the attackers. This process continues until the attackers stop interacting with the IoT device. All interaction logs are being saved for further analysis, and we reset the IoT device regularly so that they can recover from attacks. So this table shows the device we use for the experiment and their corresponding vulnerabilities. Currently, we only collect data for several IoT cameras, smart plugs, and routers. In order to better understand the attack behavior against IoT device through the attack trace, we also generate attack graph for IoT device based on the interactions between the attackers and the IoT device. So this graph is a partial attack graph against the TP-Link NC220 cameras web server over port 80. So the node represents the attacker's actions, such as probing a directory, accessing a resource, exploiting certain vulnerabilities, or uploading a malware. The edges connecting to nodes indicates that some attackers have taken another action after receiving the previous response from the IoT devices. So this attack graph demonstrates that the attackers conduct various types of pre-attack checks to gather information before really launching, before really exploiting vulnerabilities and launching attacks. For example, many attackers will check the favicon file before sending the exploit code. The attackers can identify the target device by matching the MD5 hash of favicon file with a database, or just by locating its image. So the second part is the reinforcement learning agent. The reinforcement learning agent is responsible for mimicking the IoT device. It does so by first model the interaction between the IoT device and the attackers using Markov decision process through the collected attack trace. At runtime, it will leverage reinforcement learning algorithm to select proper response to the attacker's request based on the interaction history. In the end, it will also log all attack sessions for further analysis. So as I mentioned above, the reinforcement learning first models the interaction between the attacker and IoT devices as a Markov decision process. In a traditional Markov decision process, the agent interacts with the outside world called environment through a series of actions. At each step, the agent observes the environment state and takes an action. As a result of the action, the environment makes corresponding change and transit to another state. Meanwhile, the agent may receive a reward generated by the environment. The agent will continue this process and get accumulated rewards after every action until the session is over. The agent seeks to maximize the accumulated reward by taking proper actions. In our case, the Honeypot is the agent and interacting with the environment full of different attackers. At each step, the agent observes the environment state by analyzing the attacker's request package sent to the Honeypot. The agent then takes an action to choose a proper response to fulfill the attacker's request. After sending the response, the attacker may send another request that will force the agent to enter a new state or just terminate the session by stop sending any request. A reward is collected whenever the attacker tries to exploit a vulnerability or terminate the attack session. Next, we will describe the state space, the action space, and the state transition probability quickly. So the state space of our MDP model is defined as a series of packets received from the attackers in the equation. In particular, P here represents the packets, and we classify them through parameters such as the request path or query string. In addition, we also manually add a terminate packet to the state if no new packet is receiving from the attacker after a certain period of time. The action space for our MDP model is a multi-discrete action space, which means that a different set of action is available at different state. So the state transition probability in our MDP model can be described as a transition function as shown in the slides. In the function, the S here represents the current state of the environment. The A represents the action taken by the agent, and the S prime represents the next state. We calculate the transition probability through some statistic results from the collected attack trace. In particular, the C here means the count, so we count all occurrences where at current state with certain response, the percentage of the attackers send another request that leads to the next state S prime. So for the reward function, since the primary goal of HoneyIoT is to attract attackers to launch some attacks, if an attacker terminates the session without exploiting any vulnerabilities or uploading malwares, we just assign a negative reward. On the other hand, if an attacker sends malware download command, we assign a very big positive reward. If an attacker exploits any vulnerabilities, we assign a small reward. For all other state transition, we just assign 0 as intermediate reward. So back to the HoneyIoT system, the front end is a virtual machine, opens some ports according to the type of IoT devices we are simulating. It analyzes the received request packet and sends its features like the request path, query string to the reinforcement learning agent. In addition, if the request packet contains some malware download command, the front end will send it to a separate crawler that is sandbox for malware collection. Upon receiving the response selected by the reinforcement learning agent, it will assemble and rewrite some part of the response, like the date file in the HTTP header, and send it back to the attackers. So how do we mutate the content? In order to rewrite the response, we first need to identify the mutation fields. So based on the collected trace, we find the response generated by same request to the same IoT devices at different time. So by comparing these responses, we find that some fields do not change, just like the static web content, and some fields change. So the fields change are the mutation fields. Then we classify the mutation fields into different categories based on the cause of the mutation. The time fields, such as the date file, date in the HTTP headers, the system field, such as the orientation of the IoT cameras or the switch status of the smart plug, which is usually being used in the different API calls, or some random fields that does not have a very clear mutation logic, which can be the session identifiers, encrypted values, etc. So the figure here shows how to update the mutation field with a simple example based on the specific attack request against the NC220 web camera. As shown in the figure, for the request, the date field is being rewrite with the current time of the HoneyIoT server. And for the system field, HoneyIoT randomly select valid values from the database at runtime. So for performance evaluation, we have implemented HoneyIoT camera using the attack trace of 6 different IoT cameras, and the camera Honeypot is deployed on AWS for 3 months. So in order to test how much can the reinforcement learning algorithm help, we also implement the baseline Honeypot, which is identical to the HoneyIoT camera, except that it does not use any reinforcement learning algorithm. Instead, we implement a simple heuristic algorithm that selects each valid response with equal probability based on the attack graph. We also deployed the existing Honeypot snare antenna, which is general HTTP Honeypot that can effectively mimic the web service of IoT devices after careful configuration. So after deploying them on AWS for 3 months, all Honeypots receive some attack trace. As shown in the table, the HoneyIoT camera is the most effective one by having the longest average session length, the most vulnerability exploited, and the largest number of malware collected. So this figure shows the vulnerability exploitation distribution. So if we look at the figure here, we can see that HoneyIoT did direct different attackers to different vulnerabilities that exist on different devices, IoT cameras, to maximize the possibility of attacks, which indicates that HoneyIoT can mimic different IoT cameras. The baseline Honeypot and the snare antenna cannot do so. In fact, most of the attackers collected by them are through a simple vulnerability that exists on the Reolink E1 zoom camera, which is basically the attacker can do a directory traversal attack to get the SSL key. So this figure shows the malware collected by different honeypots. So after the crawler gets the malware, we upload them to VirusTotal for malware classification. So most of the malwares collected by HoneyIoT are different type of botnet malwares. Since the source code of Mariah is open to public, a lot of attackers write their own version and create their own botnet. On the other hand, HoneyIoT also collect many coin mining malwares that are essentially scripts and miner software. the attacker just configures the software with their own digital currency wallet key, so that after mining, the profit will directly go to their own account. So these results together demonstrate that HoneyIoT camera can effectively bypass the pre-attack checks, mislead different attackers to launch their exploit code, and collect various type of malwares from the attackers. So in order to evaluate the extensibility of HoneyIoT, we also implement and deploy the router Honeypot, the HoneyIoT router, and the smart plug Honeypot on AWS, also for 3 months. So the experiment setup is identical to HoneyIoT camera. So as shown in the figure, the router Honeypot successfully direct attackers to vulnerabilities of all simulated routers except the Huawei WS7200, probably because there's no publicly exposed vulnerabilities with the WS7200. After analyzing the log, we also noticed that the reinforcement learning model avoid using the response of the Huawei router in most cases, as it does not provide any rewards. So similarly, the smart plug Honeypot direct attackers to all 6 smart plugs. So we also deployed honeypots at 3 different locations, the Virginia, Paris, and Tokyo, and perform analysis on the collected malware based on the geographic locations. So the following, like the graph, is malware collection result for HoneyIoT camera, HoneyIoT router, and HoneyIoT smart plug. The performance difference among honeypots is affected by the device type it's emulating and the attacker's behavior difference at different locations. The attacker can handcraft their mass scanner to restrict the scanning area with the goal of reducing the overall scanning time and target on specific devices that are widely used in a specific region. So as we mentioned above, before, HoneyIoT should also be robust against existing honeypot detection tools. So shortened honey score is a well-known tool to check whether the device is a honeypot or not. Given an IP address, the shortened honey score calculates the probability of the host to be a honeypot in a range from 0 to 1, where 0 means the host is definitely a real system, and 1 means the host is definitely a honeypot. After deploying HoneyIoT, we wait for a week and then use shortened API to acquire the honey score of all 3 honeypots by providing their IP addresses. As shown in the figure, HoneyIoT have a honey score of 0, which demonstrates that HoneyIoT is effective at maintaining coverness against reconnaissance and honeypot detection tools. So in conclusion, we propose an adaptive high interaction honeypot for IoT devices, which utilize reinforcement learning agent to provide proper response. And we provide high fidelity responses through content mutation. We also evaluate HoneyIoT by deploy it to the public internet. Thank you very much. Please, if you have any questions, let me know.
Any questions? Yes, one question. Let's wait for the mic to arrive there. And you tell me if you hear the question, okay?
Hello. I have a question about the reward design in your algorithm. So you said if there's an action for download or downloading or uploading malware, then you assign a large reward. And if there's other vulnerability, you assign a small reward. I was wondering, how do you decide all these values? And is your algorithm sensitive to this different combination of rewards?
Okay, can you hear me?
Yeah.
Okay, so first, we try different combination of the reward function and design it. Of course, the reward function right now is quite simple, mainly because what we focus is on collecting malwares. After trying different combinations, the algorithm is not very sensitive to the changing the values, mainly because we assign because our permanent goal, like our ultimate goal, is collecting malwares. So collecting malware get a very large response. The reason that we we have a small value for exploiting other vulnerability, like acquiring some files for the IoT devices, is because we want to encourage the attackers to come back again. So we don't want to. We think that this path, like after this path, is still useful in the future. Maybe the attackers will use this path to further upload malwares. So yes. So to your question, first, right now, after testing different reward functions, we think the whole algorithm is not very sensitive to the changing specific values of the reward function. Second is we acknowledge that the reward function design right now is not sophisticated enough, and we are trying to polish it further. Thank you.
Thank you.
Okay, let's thank the speaker again.